Hello and welcome to the part 2, how to read the character table. In the part 1, we have understood the concept of great orthogonality theorem, the various labels of irreducible representation and so on. Now, after that part where we have decided the characters for various systems, now in this section we will be talking about the Cartesian coordinates and the binary product. That is the basis function we call the symmetry of functions and the binary product. So these symmetry of functions can be generated in many ways. One of the ways is to use the orbitals as a basis. And for that, let's start using the mathematical functions for the orientations of p orbitals, px, py, pz orbitals. They're oriented in space along x, y, and z axis. So we'll take p orbitals as a basis to understand the origin of the third column in the character table. Right? Let's do it. If we talk about the symmetry operations for px orbital, and for px orbital, if we use the operations under C to B, identity symmetric for all characters, obviously this has to be plus 1. If we talk about rotation by C2 along z-axis for px orbital, so you'll find that the px would transform to minus 1. That is, the lobe of one orbit would be transformed to other. If we talk about xz plane, because we are talking about x and z that is locked in the plane itself, the character of x are not going to change, it will remain plus 1. And similarly for yz plane, because x is there and is going to change x to minus x, therefore the character would change to plus 2 minus 1. And that would support how the characters that have been derived as 1 minus 1, 1 minus 1 respectively, and we'll refer to the character table, and just referring to the character table we'll see that it actually belongs to B1. So we would say that Px transforms as B1. That is, the symmetry of Px corresponds to B1 in this particular case. Similarly, let us take Py. So Py orbital for identity, of course it is plus 1. Rotation by C2 degree along z-axis is going to change. Of course, this is minus 1. If you're talking about xz plane, y coordinates are, of course, would be reflected. So it's minus 1. And if you're talking about yz now, because it is logged in y and z plane itself, its character would be plus 1. And your characters would be 1, minus 1, and 1 respectively. That would correspond to B2 symmetry. And therefore, I would say that Py transforms as B2 symmetry. Same way you can go for z orbitals. For identity, the symmetry is the character would be plus 1. Rotation by C2 degree for z axis itself is not going to change. It is plus 1 itself. If you talk about xz plane, z is contained, so therefore characters are plus 1. If you take out yz, z is there, so its the characters plus 1. All of them are plus 1, and therefore all of these characters being plus 1, it transforms as A1. So Pz transforms as A1, and therefore XYZ orbits, p orbitals, have different transformation properties under C2B symmetry. And you can just see that for A1 it is Z, for B1 it could be X, and for B2 it could be Y. So that is how, taking B orbitals as a basis, we can derive certain observations. If we talk about the rotation of various orbitals, let's start with for the RZ. So for C2 along Z axis, the character would be plus 1. For sigma xz will be minus 1. Now just notice it. If you are rotating along the z axis, so the x would get reflected, will be changing to minus rotation. If you are rotating for sigma xz, and similarly yz, it will be minus 1, and therefore we can say that the rz transforms as a2. That's how you can also assign for various other combinations like px, like Rx and Ry, and will then begin to conclude the third component, rather fourth component of the character table. If we choose d orbital as the basis function, we just take an example of dxy in a C2B character table. For dxy, the characters are plus 1 for identity. If you rotate it in any direction by C2 180 degree, this will completely be transformed. Character would remain positive. There will be no change here. And for YZ plane, of course, if you're using a YZ plane here, then the X would get reflected and the character would be equal to -1. That's quite understandable. Similarly, xz plane would be also turning to -1, and hence we have a set of characters for identity +1, C2 +1, sigma yz -1, sigma xz -1, and they are found in the A2 irreducible representation. So the complete, so just look at we have been talking about A2, so -1 and -1, -1 and -1 here components are there, and therefore you can just conclude that A2 irreducible representation of this kind. XY transforms as this. Conclude, we can make it like that. In similar fashion, xz goes like b1 and yz goes with b2. And similarly, we can work out for dz orbitals and dx square minus y square orbitals as well. So if you do it for dz orbital under identity and C2 and sigma xz and sigma yz, there will be no change in the system. And the same is case for dx square minus y square. For identity C2 sigma xz and sigma yz, there will be no change, and therefore they would have all the characters equivalent to +1. And similarly, thus dz square and dx square minus y square would transform as A1 representation. So that's quite good understanding of the basis functions. Use basis function as x, p, x, p, y, p, z, or as orbital, or dx square minus y square, dz square, dxy, dy, z, dxz orbital is the basis function, and derive the other loop. If you use the other things, for example, last two columns can be developed by considering orbital symmetry for singular dimension S, px, py, pz as a basis for symmetry and transformation, identity to which irreducible representation does not belong. Similarly, for other columns, we take binary orbitals as the basis, and ternary orbitals also, if you want, if you are interested, you can work out for f orbitals and so on. One can now understand the theoretical importance of the character table. And more, this allows us to develop a major part of the character table. Fortunately, all such character tables are available, and we really do not need to poke our nose for constructing it. What is required is to understand logic behind all such terms, to make predictions concerning various physico-chemical properties of molecules, and support arguments to theoretical chemistry. That's it. Thanks for watching.